Alrighty, hello and good afternoon. Um, we are live. Oh man, it's hard to get better than Kendrick right now. It really is. Though I would totally love to get some new stuff. From him, but everything he has is excellent. All right, I waited today actually for my second cup of coffee so I could enjoy it right now. So here's to all of you mid-afternoon coffee drinkers. Yeah, news things. We have Kendrick Lamar is on our playlist. You can check that out for some kind of it's just good kind of chill, a little bit bittersweet vibes. It's just what was going down as I was doing lecture prep this morning. I think the biggest piece of news is that exam 1 drops tomorrow. Which technically, this is the second test, right? There's the prereq exam, but this is the first one with what's the word I'm looking for? This is the first one that's based off of chemistry, right? The first one with chemistry content. So it you already know everything it covers. Chapters 2 through 4. One thing that I do want you to know is that this weekend, and this is the case for any weekend that a test is live, because all the exams open at 12 a.m. Friday, close 11:59 p.m. Sunday, all right? So they're like a Friday through Sunday event. Hey, Kate. How's it going? And so anyways, during that time, you can expect radio silence. From me. So I can't give out any info, answer any questions, even if it's just clarification stuff about the exam. I can't. So now if you the one thing that I will say is, if you think you found a typo, totally email that to me. I can't alter an exam while it's live, but if you think you found a typo, let me know. I'll investigate those problems. You may be rolling your eyes skeptically because I still haven't investigated the prereq exam problems. I will be getting to those soon, I promise. I've just been grinding to keep all the things that we need for the class up to date. Homework 5 just went live this morning, so I'm trying to give those of you who like to work ahead as much leeway as possible. I will be getting back to that, the typos on the prereq exam, correcting those soon though. If you think you find one on exam 1, totally let me know, but it's something that I correct after the fact, not something that I can correct live. Any free response? Okay, Prathana, great question. There are no free responses in exam 1. I don't think. I can double check that. Let's see, go over the quiz next week. Yes, we totally can. Also, that's another thing to point out. We have office hours today. Right after class from 3 to 6. So this is a great chance. This is kind of like last hurrah to get in there, ask me some questions before exam 1 opens and I go silent. So we'll have an after party for lecture in office hours today. Okay, let's see. So the exam is just Esther, the exam is multiple choice. Fill in. I'll double check this on when we head over into office hours. Ask me again, because what I'll do is I'll open up the exam and look at because I can't remember exactly all the problem choices. I think there are some like where you have to calculate the answer and like punch in the number. So I think there's some numerical entry, some multiple choice. I can't remember if I did sorting problems or not. So we can get to that in office hours. And I can let you know explicitly, because I will have the time to open it up and check what problem types are in there. All right. Okay. With that being said, we need to look at, continue our journey through Chapter 6, which we began last week. Chapter 6 is all about stoichiometry, and we're just going to keep rolling, keep rolling with that. Now, we saw that, again, just to freshen our memories, stoichiometry is a weird word. It's a word that's unlike any other word that we use in English, but really, what stoichiometry is about is it's about unit conversions. All right, it's about unit conversions, transitioning between the units of atoms or molecules, right? Transitioning to moles, transitioning to grams, right? And the conversions between these two, to go back and forth between atoms and molecules to moles, this is where you use Avogadro's number, right? Whoa, there we go. This is where, we use 6.022 times 10 to the 23rd things, right? It could be atoms or molecules in 1 mole. That's how you move back and forth. Whoa, Photoshop is being crazy today. Okay. Is it moles for molecules? So Jen, Avogadro's number can be used to convert between number of molecules or atoms into moles. Remember, 1 mole is just 6.022 times 10 to the 23rd things. So that could be 6.022 times 10 to the 23rd molecules or atoms. Either one of these. Either molecules or atoms can be represented here in this unit conversion. All right, but 1 mole is 6.022 times 10 to the 23rd things, whatever things we happen to be dealing with. All right, and to go back and forth between atoms and moles, or molecules and moles, you use Avogadro's number as the unit conversion. To move back and forth between moles and grams, you remember that AMU is the same thing as grams per mole, right? And so we can use the periodic table to convert from grams to moles. Okay, Jen. Sorry. Now I understand. Now I understand your question. Okay, here, let me, rather than type it, let's use a slide. So moles, when we talk about moles does not equal molecules. One mole is equal to this number, Avogadro's number's worth of molecules. So this many molecules is 1 mole of that substance. So for example, well, also 1 mole is equal to 6.022 times 10 to the 23rd atoms. 1 mole could also be equal to 6.022 times 10 to the 23rd ions. All right, it could be any number of things, but the important part is moles. When you have 1 mole of something, you have this number of things. All right, it could be atoms, it could be ions, it could be molecules. It depends upon the problem. But whenever you have 1 mole of something, it's that many things. And let me know if that makes sense. But that's what we're talking about when we talk about moles. When 1 mole is like a pair. A pair is 2 things. 1 mole is like a dozen. 1 dozen is 12 things. 1 mole is 6.022 times 10 to the 23rd things. It's the same idea as a pair or a dozen, only much larger. Okay, so again, whoops, I didn't mean to open that one. There we go. You can move between particles, number of particles, atoms, molecules, ions, to moles using Avogadro's number. Okay, good. I'm so glad. And then you can move from moles to grams using the atomic masses found on the periodic table. All right? And we did that yesterday. We found out how many carbon atoms are in 5 grams of carbon. We found out what mass 4.16 times 10 to the 24th atoms of oxygen would have. But now we're going to take this one step further with the following example. Determine the number of molecules present in 2.0 grams of ammonia. All right? In 2.0 grams of ammonia. Now, anytime you're starting with a mass and moving to molecules, we're going to have to do this in 2 steps. It's going to begin by taking the mass of ammonia and converting it to moles, right? We're going to put grams of ammonia in the denominator, moles of ammonia in the numerator. And then the second step, once we've converted to moles, is we'll put moles of NH3 in the denominator, and we'll put molecules of NH3 in the numerator. All right? Now, in order to convert, so we've set up the unit conversions, but we need to add the numbers. This one right here, this last one, we'll use Avogadro's number because we know 1 mole of ammonia means that we have 6.022 times 10 to the 23rd molecules of ammonia. All right, that's Avogadro's number. For our second unit conversion, we need to look to the periodic table. All right, we have to look to the periodic table. Now, in the previous examples, we just looked up the atomic mass of nitrogen, or in the previous examples, we looked up the atomic mass of carbon, the atomic mass of oxygen, and used that to convert from grams to moles. But no matter how hard you look on the periodic table, you will not be able to find NH3. The reason is the periodic table has all the elements, but NH3 is not an element, it is a molecule, right? There is one nitrogen and 3 hydrogen present, and so what we need to do is we need to calculate the unit conversion here based on the individual masses of nitrogen and hydrogen. So for example, nitrogen has a mass of 14.01 AMU. Hydrogen has a mass of 1.008 AMU, and here in this molecule we have 3 hydrogen, right? So we need to calculate these, we need to add these together to calculate what we call the molecular mass of nitrogen. So 1.008 times 3 is 3.24 plus 14.01. So this means that ammonia, NH3, has a molecular mass of 17.034. When you look at sig figs, based on the numbers I'm using, we'd have to round to that place, the second decimal place. So this would be 17.03 AMU. All right. And remember, if you're going, why are we doing this again? Remember, AMU, atomic mass units, is the same thing as saying 17.03 grams of ammonia are in 1 mole. All right? This becomes the unit conversion. Corinne's a great question. Okay, so Corinne's question asked, wait, doesn't the periodic table show hydrogen as 1.01 AMU? It totally depends on the periodic table. Some show 2 decimal places, some show 3, but it doesn't matter which you use. The numbers that you get will be comparable. But I think you're right. I think our book shows 2 decimal places. Now, Jen, yes, we are looking for molecules, but to get there, we need to know the AMU for ammonia, NH3. You can totally use 1.1, yes, because the reason why you need to know that is because we need to know how many grams are in 1 mole of ammonia, so we can convert here and cancel grams NH3, cancel with grams, and then moles of ammonia, cancel moles. And now that molecules is the only unit left, we can crunch our numbers and figure out what how many molecules of ammonia we're dealing with. All right, so here we go. 2.0 divided by 17.03 times 6.022 times 10 to the 23rd will give us a value of 7.072255 times 10 to the 22nd. In our initial problem, given our initial numbers, our mass had 2 sig figs. That'll limit our answer to 2 sig figs. So that 7, this 7, is going to round up. So our answer will be 7.1 times 10 to the 22nd molecules of ammonia is our correct value with the correct units with the correct sig figs. All right. Now I have a question, a practice problem for you to do that I'm going to write up on the board, but I'm not going to do this one now. I'm going to ask you to give this problem a try on your own. And see if you can do it. This problem is kind of a next level challenge. This is an example of a problem that would be like exam caliber. Now, when I say exam caliber, I'm talking about exam 2, right? Chapter 6 is not on the first exam. But if after you take the first exam, you start studying chapter 6 again, you want to test your mettle, this is the problem to check out. So give this a try. All right. How many molecules are there? How many molecules are there in 2.0 liters of water if the density of water is equal to 1.008 grams per milliliter? All right, so this is kind of a next level challenge. Give this a crack in your free time. Bring it up in office hours later. We can do it together. But see if you can solve it on your own. If you can, know that you're getting to the point. You're ready to kind of handle the next level challenges that you'll face on the second exam. All right, so give that one a try in your free time. We're about to transition a little bit, so we've introduced the concept of moles, how to use moles to convert between atoms and mass and atoms, or even mass and molecules and mass. We've seen examples of those. But now, let's take a look. We need to talk about, chemical equations. All right, so let's take a look at chemical equations. All right, so here's the deal. When we talk about chemical equations, there's a general format that we present these. These are chemical reactions, transformations, etc. And the way these are presented, there's kind of like a format, a nomenclature, a grammar, if you will, to the way we write chemical equations. So generically speaking, we write chemical equations with the reactants on the left side of the equation, and then an arrow, and the products. Sorry, reactants on the left side, products on the right. The reactants combine, they react, they rearrange, and they form the products of the chemical equation. So, for example, if you were to write the reaction for the combustion of hydrogen gas, it would look like this. You have, in the combustion of hydrogen, hydrogen gas reacting with oxygen gas to produce water vapor. All right? And you may notice these little dudes hanging out right here. These are called phase symbols. And they tell you what phase of matter each reactant and product is in. All right, so G is for gas, S is for solid, L is for liquid, and AQ is for the aqueous phase, which just means dissolved in water. O2 is oxygen gas. It's one of the homonuclear diatomics. All right, so you've got your phase symbols here. Your hydrogen and oxygen are the two reactants in this chemical equation. There's only one product here. The sole product of this reaction is water. And so this is kind of how chemical reactions are presented in the form of chemical equations. Oops, let's get rid of that. There we go. We've got reactants and products separated by the arrow, and a phase symbol for each reactant and product letting you know what phase of matter they're in. Now, as this reaction is currently written, there is a problem. All right, there's a problem with the combustion of hydrogen as I have it written down. I'm just gonna copy it over to this new slide. All right, if you look at the number of atoms on each side of this equation, on the reactant side, we have hydrogen and oxygen. And yes, exactly, Prathana, you hit the nail on the head. And you'll see, I'm about to answer that question in this explanation. So here's the problem, and you've put your finger on what the problem is. You'll notice that there are two hydrogen atoms and two oxygen atoms on the reactant side. All right, but then when you go over to the product side of this chemical equation, you'll notice that there are two hydrogens. Yes, you are a little bit early. And only one oxygen atom. All right, so we only have one oxygen atom on the product side, and here's the problem. All right, here's the problem. Matter cannot be created or destroyed. Right? Matter cannot be created or destroyed, and yet here we start with two oxygens and we end with one. Where did it go? Well, the answer is it didn't go anywhere. We did not destroy an oxygen in this chemical process. The problem here is this reaction is unbalanced. We say that this is an unbalanced chemical equation. All right? And it is horribly wrong. An equation can't be unbalanced because matter cannot be created or destroyed. When you're presented with an unbalanced chemical equation, you must balance it. All right? You must balance it because, again, matter can't be created or destroyed. Here's how you balance a chemical equation. All right? When you go about balancing a chemical equation, you're never allowed to mess with the subscripts. All right? You have to leave the subscripts alone. The only thing you're allowed to change, you're allowed to change the coefficients in front of each species in a reaction. All right? Because that just says you're changing the number of that molecule present, but you're not changing the structure of that molecule. So, for example, you'll notice that we have 2 oxygen on our reactant side. We need to make sure that we have 2 oxygens on our product side. So we can do that if we multiply H2O by 2. All right? If we produce 2 water molecules in this chemical equation, you'll notice that now we don't just have 1 oxygen on our product side, we have 2, but it also changes our hydrogen count. All right? Now we have 4 hydrogen on the product side, and you may be looking at that and going, well, that seems like we just robbed Peter to pay Paul, right? We created the same problem that we fixed. How is this helpful at all? Well, it's not helpful for hydrogen, but we balanced oxygen. Now let's take a look at the hydrogen situation. So here we have 4 on our product side. We only have 2 hydrogen on our reactant side, and we need the same number of hydrogen, right? Hydrogen doesn't appear out of nowhere. We have to have the same on both sides. To get 4 hydrogen on the product side, we can multiply H2 by 2. And now we have 4 hydrogen on both the products and reactants side. We have 4 hydrogen on the 2 oxygen on the products and reactants. So this chemical equation, as written right here, is the balanced chemical equation. Balanced chemical equations have the same number of atoms on both the products and reactants on both the products and reactant sides. All right? And that's your quest. All right? You have to balance the chemical equation. You can't do it altering the subscripts. You can only do it altering the coefficients in front of each species in the reaction. Something that I want to point out. So here's our balanced chemical equation. These numbers right here, these are called stoichiometric coefficients. All right, that's their name. And if you're going, wait a minute, why did you say that there's a stoichiometric coefficient here? Anytime there isn't a stoichiometric coefficient written, it's automatically the number 1. All right, so you only write a stoichiometric coefficient if it's greater than 1, but if there's not one written there, it's implied. Cool? These are the quantities that you manipulate to balance your chemical reaction. Yeah. Okay. Questions so far? All right. In the absence of any questions, let's go ahead and dive in and start doing more examples. We are going to, with all of these, we're going to, oops. Write balanced chemical equations for each of the following. All right? So let's write balanced chemical equations for all of the following reactions. The first one we're going to look at is the reaction between solid sodium and aqueous HCl. This reaction produces hydrogen gas and sodium chloride in the aqueous phase. All right. Now, anytime you need to balance a chemical equation, this is how I recommend doing it. There are some people who, with their brains, they can just look at a chemical equation and understand what numbers need to go where. And if you're one of those people, that's awesome. More power to you. My brain doesn't work like that. All right. So the way I do it, and if you're new at this, if this is you're finding this particularly challenging, this is how I would recommend that you start. I start by making an inventory of every type of atom on both my reactants and my product side, because doing this kind of gives me a visual cue to see where I need to balance things, which things are out of balance, what I need to increase. So on my reactant side, I have 1 sodium, 1 hydrogen, and 1 chlorine. On my product side, I have 1 sodium, 2 hydrogen, and 1 chlorine. So right now, the only thing that's out of whack is my hydrogen, and the only species with hydrogen on my reactant side is HCl. So if I want 2 hydrogens on my reactant side, I have to multiply hydrochloric acid by 2. This will balance my hydrogen, but you'll notice a common theme here. This throws my chlorine out of balance. All right, so we fixed one problem by creating another. Now I have 2 chlorine on my reactant side, and I need 2 chlorine on my product side. The only species with chlorine on my product side is sodium chloride, so I need to multiply NaCl by 2. This will balance chlorine, but throws sodium out of balance. All right? Now, I need to figure out my sodium situation. I have 2 on my product side, only 1 on my reactant side, and the only thing with sodium on the reactant side is just solid sodium. I need 2 of them. I'm going to multiply sodium by 2. And you'll notice now my entire chemical equation is balanced. I have 2 sodiums, 2 hydrogens, and 2 chlorines on both my reactants and my product side. So this is my balanced chemical equation. All right. It may be disconcerting right at first when you are messing up one element to fix another, but you just got to push forward. Eventually, you'll make it to your happily ever after. All right. Should we pay attention to the phase symbols? Carenza, great question. When you're balancing, you can ignore them. Phase symbols will become more important in chapter 7, 8, 9, 10. So yeah, phase symbols don't have any impact on balancing. They will become important in chapter 7, chapter 8, chapter 9, and chapter 10. And when you get there, you'll see how they become important, why they become important. I'm mostly including them right now just to get us used to seeing them. But they don't actually impact how you balance your chemical equations. All that matters are the number of atoms on either side of the equation. Okay. That was a great question. Let's do our next example. Yeah, totally. So more to come in the future. Let's balance the reaction between nitrogen gas and hydrogen gas to form a familiar face ammonia. All right. Again, I'm going to begin by taking an inventory on both sides of this equation. I have nitrogen and hydrogen. On my reactant side, I have 2 nitrogens and 2 hydrogens. On my product side, I have 1 nitrogen and 3 hydrogen. All right. Now, here we have a little bit of a pickle. You'll notice that one of these looks easy to do, and one of them looks harder, right? When you look at nitrogen, you can see, oh, 1 goes into 2 evenly. That looks doable. But 3 doesn't go into 2, and 2 doesn't go into 3 evenly. That looks like a mess. Here's the cool thing. When you're balancing chemical equations, this is the one golden opportunity life gives you. And really, I mean, this is a once-in-a-lifetime situation, so be glad that you're taking chemistry. When you're balancing chemical equations, it is the only time in life when taking the path of least resistance helps. All right? So procrastinate the thing that doesn't make sense. Do the easy stuff first, and trust me, the hard stuff will work itself out. So we're going to ignore the fact that 2 doesn't go into 3, and we're going to focus on the fact that 1 goes into 2. All right? We need 2 nitrogen on our product side, so we're going to multiply ammonia by 2. This balances nitrogen, changes our hydrogen count, but we're not really that concerned because hydrogen wasn't balanced anyway. All right, now look what just happened. 2 does go into 6 evenly, right? 2 goes into 6 3 times. So let's multiply H2 by 3. And now we have 6 hydrogens on both sides of the reaction, reactants and products, 2 nitrogen on the reactants and products. This is your balanced chemical equation. All right? Let's do another one. Let's do another example. You'll find that I'm doing a lot of examples with balancing chemical equations because you will be doing a lot of examples of balancing chemical equations. This practice comes into just about every single stoichiometry problem that you're going to do. So you need to get really, really, really good at this. All right? So let's look at this reaction between dinitrogen tetrahydride in the aqueous phase and oxygen in the gas phase to produce water vapor and nitrogen gas. All right? We have 3 elements in the mix: nitrogen, hydrogen, and oxygen. On the reactant side, we have 2 nitrogen, 4 hydrogen, and 2 oxygen. On the product side, we have 2 nitrogen, 2 hydrogen, and 1 oxygen. All right, it doesn't matter which one you pick. I'm just going to go with oxygen because it looks really simple. Here, we need 2 oxygen on the product side because we have 2 on the reactant side. So let's multiply water by 2. This balances our oxygen count and changes our hydrogen count to, well, hey, look at that. We actually balanced oxygen and hydrogen in one foul swoop. Oxygen and hydrogen are balanced. Nitrogen is already balanced. This is your balanced chemical equation. All right, now you may be rolling your eyes a little bit, doing that thing where you're like, oh, I hate when the professors take the easiest examples for themselves because the ones that they give to us are hard. Listen, there are a range of difficulty levels for balancing chemical reactions, but most of them just unfold naturally like you've been seeing here. The problems that I've been doing could all show up on the exam. They're all exam caliber. They're all the types of reactions that you could be asked to balance, all right? And the other cool thing is if you do your job right, you do kind of get that Disney happily ever after moment at the very end of the problem where everything just seems to work out, unlike any other thing in life, right? So again, savor it. It's special. All right, now, what happens when things get bad, right? What happens when things get difficult? There is a situation when balancing chemical equations that's harder to handle than the usual, okay? And I'm going to teach you a technique for handling those next level problems on an equation that you don't need this next level technique, all right? So I'm going to teach it on a problem, and you're going to be looking at it going, why are you teaching me this? I could just do this in my head. Just hang with me, learn this method, because the problem that comes after, you probably won't be able to do in your head. So we're going to learn it on an easy example and then apply it on a next level one. Cool? Okay, so let's take a look at the decomposition of aqueous hydrogen peroxide into water and oxygen gas. This is liquid water and oxygen gas. All right, we're going to do our thing, hydrogen and oxygen on both sides of this equation. On the reactant side, there are 2 hydrogen atoms and 2 oxygen atoms. On the product side, we've got 2 hydrogen atoms, and then we have 1 plus 2 oxygen atoms. Now you're going, well, isn't that 3? The answer is yes, but for problems where you have the same atom coming from more than one source, here oxygen is coming to us from both water and oxygen, right? We have 1 oxygen coming from water, 2 oxygen atoms coming from oxygen gas. I find that it's easiest to write these broken up as 1 plus 2 when you're balancing, and I'll show you why in just a second. All right, so you'll notice here in this equation that hydrogen is balanced. All right, hydrogen is balanced. I would prefer not to mess with hydrogen at all. The problem is we have 2 oxygen atoms on our reactant side, and we have 3 oxygen atoms on our product side. All right, and we need these to be equal, and they're not, and they don't go into each other evenly, and it's a pain. What we're looking for is we need to multiply O2 by some number, right? If we can multiply O2 by some number so that the number of oxygens on both sides of this equation are equal, then we've got it made. And if you're wondering, well, what is that number we should multiply O2 by? We have an equation here. We can solve it. Let's start by subtracting 1 from both sides of this equation. That changes it to 1 is equal to 2 times n. And now let's divide 2 by both sides to solve for n. So that number we need to multiply by is 1/2. And watch what happens when you add this in. Sorry. It's okay. You need to get something?
Yeah, I just need to grab.
Okay.
Sorry.
Oh yeah, no worries.
I love you.
Yeah. Love you, babe. Okay. So this number is 1/1/2. Now watch what happens when we add this to our balanced chemical equation, or to our unbalanced chemical equation. If we put a 1/2 in there, then 2 times 1/2 is equal to 1. And 1 plus 1 is equal to 2. By adding this fraction, we have balanced this chemical equation, right? Because now we have 2 oxygen on our reactant side, 2 on our product side. Same with hydrogen. Here's the problem. The problem is you can never leave a fraction in a balanced chemical equation. All right? We can use fractions to balance, but we can never leave a fraction in a balanced chemical equation, because the reason for this is a balanced chemical equation displays the simplest whole number ratio between reactants and products, and a fraction is not a whole number. So we can use the fraction to balance the chemical equation, all right, but we can't leave the fraction as part of the chemical equation. Now, if you're sitting there wondering, well, if we can't leave it there, then what are we supposed to do? I'm about to show you. All right. So what you do is we inserted the fraction. It's technically balanced, but we have to undo what we did. And the way you do that is multiply the entire chemical equation by your denominator. All right. When you do this, when you multiply the whole equation by your denominator, we're going to distribute this 2 in to every reactant and product. When you multiply 2 by hydrogen peroxide, you get 2 molecules of hydrogen peroxide. Decomposing into 2 molecules of water. Whoa. There we go. Sorry about that. Photoshop freakout. Plus, now when you do 2 times 1/2, it's just 1 O2. And this is, whoops, our balanced chemical equation. All right, here's the critical thing to remember. For balanced equations, balanced chemical equations always display the simplest whole number ratio or ratios between reactants and products. All right? You can use a fraction to balance a chemical equation, but you cannot leave it in your final answer. Cool? All right, now, if you're looking at this example and going, okay, yes, but I could have done that one in my head. I didn't need that weird method, so you're tempted to ignore the weird method. Let's do the next problem, because this one is harder to do in your head, and knowing how to use fractions will prove helpful. Let's look at the combustion of hexacarbon hexahydride, better known in organic circles as benzene. All right, this burns to produce carbon dioxide and water. Oops, not liquid water. Water vapor. All right, now let's balance this chemical equation. We have carbon, hydrogen, and oxygen on both sides of our equation. Carbon, hydrogen, and oxygen. On the reactant side, we have 6 carbon, 6 hydrogen, 2 oxygen. Product side, we have 1 carbon, 2 hydrogen, and then 2 plus 1 oxygen atoms. All right? Now, as I said before, always balance the easiest stuff first. And the easiest thing to jump out to me is carbon. We have 1 on the product side, 6 on the reactant side. The only way to get 6 carbons on our product side is to multiply CO2 by 6. You'll notice that this balances our carbons, and changes our oxygen counts. So now we have 12 plus 1. This is another reason why I keep the oxygen separated when it's coming from 2 different sources. It makes the multiplication easier. Let's look at hydrogen. Looks like the next easiest to handle. We've got 6 on the reactant side, 2 on the product side. If we multiply H2O by 3, we balance our hydrogens. So 2 times 3 is 6, and now 1 times 3 is 3. So we have a grand total of 12 plus 3 oxygen on our product side. And here's the bummer. 2 does not go into 15 evenly, right? 2 does not go into 15. What we need is we need to multiply O2 by a number, right? So we don't disturb carbon or hydrogen. Multiply O2 by some number so that 2 times that number is equal to 15. All right? Now, what is this number that can make 2 equal to 15? Well, let's do some algebra and find out. That magic number happens to be 15 over 2. Watch what happens when we add it in. When we add in 15 over 2, multiply O2 by 15 over 2, we get 2 times 15 halves equals 15. And as of right now, oxygen is balanced, hydrogen is balanced, carbon is balanced, everything's balanced. We're good, except we have a fraction in our chemical equation, right? We cannot add a fraction and leave it there. So we need to multiply our entire chemical equation by our denominator. And we will distribute this to every species on both the products and the reactant side. All right. Once we do, we'll have our final answer for the balanced chemical equation. It'll give us 2 molecules of benzene, C6H6, plus 15 molecules of O2. Oh, sorry, this is gas. Produces 2 times 6 is 12 molecules of CO2 gas, plus 2 times 3 is 6 molecules of H2O. Vapor. All right, so this is the balanced chemical equation for the combustion of benzene. All right. There is, well, I was about to say there are tons of problems on balancing chemical equations in the practice homework. Also, the homework 5 is up there, which is based on chapter 6. Not due for a little while. I was gonna say, like, oh, go ahead and do a bunch of these over the weekend. You're not gonna be doing that though. You're gonna be probably studying for exam 1, and you should be. So you'll probably get to these sometime next week, Monday maybe. All right, here's how I want to end things. I want to end things with kind of a teaser, a foreshadowing of where we're going and where we're going to spend the bulk of our time for the remainder of the course, doing this one thing. You're about to see it. Your terrifying apocalyptic vision of the future. All right, it's coming here. I want you to consider, again, circling back to where we started, as all good stories do. If you want to watch an example, if you want to see an example of a great story that circles back on itself, go watch The Prestige, which is the movie Susan's in, this weekend, if you have time, when you're not taking your test. Let's circle back to the combustion of hydrogen and consider something. So, let's read this chemical equation. It says 2 molecules of hydrogen react with 1 molecule of oxygen to produce 2 molecules of water, right? 2 molecules of hydrogen react with 1 molecule of oxygen to produce 2 molecules of water. All right, here's my first question. If you start with 3 molecules of O2, how much water do you make? Well, if you look at the ratio, it's a 1-to-2 ratio, right? So if you start with 3 molecules of oxygen in this reaction, you're going to make twice that. You're going to make 6 molecules of water, right? That makes sense. I've got another question. If you start with 3 dozen oxygen molecules, how much water will you make? Well, again, it's a 1-to-2 ratio. So if you start with 3 dozen molecules of oxygen, you're going to make 6 dozen water molecules, right? It's just math. Now, if you start with 3 moles of O2, how many, or I should say how much, just like I've been asking with the rest of them. How much water do you make? And the answer is, if you start with 3 moles, because it's a 1-to-2 ratio, you're going to make 6 moles of water. And this is where everything blows up. All right, the stoichiometric coefficients. Here, I'm just rewriting the equation here. Right, and remember we've got a implicit 1. The stoichiometric coefficients in a chemical reaction represent molar ratios. And when I say molar ratios, I mean, i.e. the number of moles. They represent molar ratios between reactants and products. All right? And because of this, we can use them to calculate quantities of reactants and products for chemical reactions. And that is awesome. This is the living, beating heart of everything we'll be doing from here on out. All right? With that kind of bomb of knowledge, I'm going to put a pin in lecture right here. Okay, so this will be the end of lecture for today. We will pick up on Monday using our stoichiometric coefficients, our newly found molar ratios, to do tons of calculations with lots of sig figs. It's going to be awesome. We're going to be crying tears of joy, possibly pain, on Monday, but we're going to be doing it together. All right, and that's what's important. So we're going to pause lecture here. So that's it for this week. We're going to pause, take a 30-minute break. I'm going to shove some food in my face, and maybe make a fresh cup of coffee, and then we'll be back here starting at 3 for office hours, 3 to 6, which will be our last chance to get into things before the exam drops. So to everybody who came out and participated, thank you. For those of you who are planning on hanging out for office hours, I'll see you soon. And for everyone who I don't see, good night and good luck on the exam. Maybe I'll catch you in office hours. All right, catch you in a few. Bye.